last in this mini series. So yeah, thanks.
Okay, thank you. So first of all, let me share some references. So I was asked for some references yesterday, and so this is the master thesis of John, which covers all the material that we've seen in the first lectures. I really recommend this. Okay, so now let me share. Okay, so we should see it now. Is that okay? Okay, so today is the fourth lecture of the mini course about blowups, Gale duality, and moduli space. And we are going to discuss the moduli space of the blowup of Pn in m+4 points. So this variety can be realized, as we will see today, as the moduli space of vector bundles on certain rational surfaces. And to construct the rational surface from the point set of n+4 points in P4 and Pn, we will use the construction of of the Gale duality that we saw last time. So let me just recall this construction. So this associates to a set of M. M here is R plus S plus 2 points in PR, a set of R plus S plus 2 points in PS. And as I explained last time, this is how it goes. You start with your points in the projective space PR, and you write its coordinates as vectors on a matrix. After some change of coordinates, you may assume that the first R plus 1 vectors are just forms the identity matrix, and then you just complete with the matrix A. And then you take the transpose of this matrix, and in this way you get your R plus S plus 2 points in the projective space PS. Okay, so in the case when you have n+3 points in P1, this is a very classical construction. You associate to a P1 with n+3 marked points. It's a rational normal cubic that is obtained by the Veronese embedding, and then just look at the image of this n+3 points. And in general, this was used to study the blow up of Pn in n+3 points. So as this is the theorem that we discussed in the second lecture, a blow up of Pn is at m points is a Moiridt space if and only if the number of points m and the dimension of the space n satisfy these constraints. So in particular, you can look at the case when you can blow up as many points as possible and still have a Moiridt space. So for instance, when n is at least 5, you can blow up n+3 points. And then Mukai observed that the blow up of Pn in n+3 points can be realized as the moduli space of parabolic vector bundles on P1 with n+3 parabolic points. So this is what we discussed last time. You take the weight vector 1/2, 1/2, and this corresponds to this blow up. And then also you can look at when you have 4 points, then there is one more possibility. So for any value of n, you can blow up n+3 points and get a Moiridt space. But if you take n equals to 4, you can blow up one more point. So n+3 would be 7. And then you can blow up one more point and get another Moiridt space. And Mukai again observed in 2001 that this fourfold can be realized again as a moduli space. So this, as I said, was observed in Mukai in 2001, but it was, this construction was carried out in great detail by Casagrande, Codogni, and Fanelli in 2019. What they did then is to show that in the case when you have 8 points in P4, you can look at the Gale dual points. So you will get 8 points, you start 8 points in P2. Then you look at the Gale dual points, you get 8 points in P4. And this blow up of P4 at 8 points can be realized as a moduli space ML. So I will explain what this L is, but the idea is that this L is going to be, so this is, the L is going to be a polarization in the surface that is obtained from P2 by blowing up 8 points. And so you, when you fix this polarization in certain invariants for the vector bundle, you get this moduli space. And then what Mukai and then Casagrande, Codogni, and Fanelli observed is what happens with the moduli space of vector bundles on the surface P2 blown up at 8 points when you change the polarization L. So as we will see, there will be some hyperplanes in the space of polarizations for which when you cross this hyperplane, the moduli space is going to change. And then we can understand what happens with the moduli space when you do the change of polarization. And in this way, Mukai and then Casagrande, Codogni, and Fanelli were able to understand the funnel fourfold that was obtained from some small modification of the blow up of P4 in 8 points. So to be very concrete, if you start with the blow up of P4 in 8 points, you can flip the strict transform of the lines Lij passing through any two of the 2 points. After you flip these lines, you can also flip the strict transform of each of the 8 rational normal curves passing through 7 of the points. So you blow up the strict transform of the lines, then you you flip the strict transform of the lines, then you flip the strict transform of the rational normal sectics, and then you get to this funnel model. So let me explain how we do this in general. And so this is a more a recent work with Ana Maria Castravet, Inderkauer, and Diletta Martinelli. We proved that this construction actually works for any number of n, and any set of n plus 4 points in very general position on P2. So if you start with this points in general position in P2, then you can take the Gale dual points, and as what we will see is that for a special choice of polarization on the rational surface L, we can realize the blow up of Pn at n plus 4 points as the moduli space of vector bundles on P2 for certain invariants. Okay, so this is what I am going to explain to you today. So this is, I'm going to give you a sketch of this proof. This is not complete, but at least to give you an idea. So this is the setup. We start with our n plus 4 points in P2. You take the Gale dual points in Pn, and here we are going to be looking at the blow up of P2 at the points Pi and the blow up of Pn at the points Qi. And I hope that we don't confuse these blow ups. So to fix this notation, I'll use different notations for the surface S and for the n-fold X. So I would denote by S the blow up of the P2 at the points, and I would denote by X the blow up of Pn at the corresponding Gale dual points. And here I will use the lowercase letters for the divisors on the surface. So I will use a lowercase h for the pullback of the hyperplane section of P2, and the lowercase ei's for the exceptional divisors. In this case here, this is the expression for the canonical formula. And on Pn, I will denote by capital H, the pullback of hyperplane section, and then by capital EI, the exceptional divisor over the blown up points. Okay. And the idea now, I'm going to explain to you how we construct moduli spaces of vector bundles on the surface S. And for that, to construct this vector bundle, so first of all, we will have to fix the numerical invariance of the vector bundle. So in this case, we'll always fix the rank, the first Chern class and the second Chern class. So this will be fixed. And then to get a moduli space, we will define a stability condition. And this stability condition is always defined in terms of some ample line bundle L. Okay, so in this case, let's then, and now let me introduce this moduli space in general for any surface S and for any line bundle L. In fact, we will not only look at vector bundles, but we are going to look at torsion-free sheaves on S. So this is going to be in general, this is more general. And then given a polarization L, we will define a stability condition with respect to L as follows. So first we define the slope of a torsion-free sheaf with respect to the L. So this is just the degree of the line bundle measured with respect to L. So that is L intersect the first Chern class of the vector bundle divided by the rank. And so if you have not, if you have never seen this, you probably have seen some version of slope definition. But what you should keep in mind here is that when you have the definition of slope, whenever you have an exact sequence of objects like this, so I have a torsion-free subsheaf of E with torsion-free quotient Q, then either you have that the slope is strictly is increasing, possibly, and then if it is either strictly, I should say that it's either always equal or strictly increasing or strictly decreasing. So the slope in an exact sequence, the slope always increases, decreases, or stays the same. And now we say that the torsion-free sheaf is semi-stable if for every torsion-free subsheaf, the slope is of F is less or equal than the slope of E. And we say that it is strictly stable if you actually have strict inequality. So this is the definition of what we call slope stability. And also there's another definition introduced by Gieseker. So we say that E is Gieseker semi-stable if instead of using the slope, we use this other version of the slope, which is the Hilbert polynomial of some twist of F for some sufficiently large exponent of L divided by the rank. So we replace the intersection with L with the Hilbert polynomial. So this would be measuring the Hilbert polynomial. Okay, the Hilbert function of these sheaves. So this is the notion of Gieseker semi-stable and Gieseker stable. And usually we have these implications. So slope stability implies Gieseker stability, which implies slope semi-stability, which implies Gieseker semi-stability. Okay, so, and here, okay, so now in this situation here, in our situation, we have the P2 blown, the surface is going to be P2 blown up at n+4 points. And these are the magical invariants that we are going to fix. The rank is going to be true. The first Chern class that we are going to fix is the anti-canonical class, and the second Chern class is true. And I will try to explain this. So this looks like magic. And in a sense, these are the invariants that work, and I will justify why. And now then, when we vary the stability condition, we are going to get different different stability conditions and then different moduli spaces. So for any fixed stability L, we denote by ML the moduli space of Gieserke semi-stable torsion-free sheaves on S, satisfying those magical, having those magical invariants. And inside this moduli space, we can look at the subset formed by strictly stable, Gieserke stable objects, and they form an open subset. And let me just say some generalities about this moduli space. So in general, this moduli space, if I choose, depending on will depend on the polarization. If, as we will see later, if you choose a certain polarization, this moduli space is going to be empty. But let's suppose that we have some non-empty moduli space, and let's suppose that we have a stable, an element in the stable open subset, in the open subset of stable elements. So let me take a stable torsion-free sheath, and let's assume, for simplicity, that this E is locally free. And now this is going to be something important. I don't want to take any polarization. I take now a polarization L that has a negative intersection with the canonical. So this, let me also impose this condition. And then, okay, then by Sally duality, the X EE is going to be isomorphic to the dual of the home from E to E tensor K. And now, because the polarization is such that L intersect K is negative, the stability will imply that you have no such home, because any home from any, if you have a, as I said, if you have a map from E to E tensor K, the stability must either stay the same or decrease, but then the condition that L intersect L is negative will force that there is no homomorphism. And so from the general theory of moduli space of torsion-free sheaves, then that will say that the moduli space is smooth at the corresponding point, and the dimension of this moduli space can be computed as the dimension of the X1 from E to E. And now this can be computed using Riemann-Roch. And this is going to be, so as I said before, this is because the H0 is 1, because we are in the case of a stable bundle. So the H1 is 1, and the X0 is 1, and the X2, as we saw before, was 0. So this is 1 minus the Euler characteristic. And that Euler characteristic you can compute using Riemann-Roch, and now here's where you use those magical numerical invariants. And then if you compute, well, this is 5 minus K squared. If you compute the canonical class square, then you get that this is precisely N. So for this magical choice of invariance, you get that when the moduli space is non-empty, and when you have some stable object there, then the dimension is exactly equal to N. And the theorem is that when I take my ample in a very suitable way, then this moduli space is precisely the blow up of Pn at n plus 4 points. And so for the rest of my lecture today, what I will explain is a sketch of the proof of this theorem. Okay, so this is what we are going to prove next. And so let me just give you some steps of the proof. So first of all, I would like to analyze how a strictly, suppose you have some strictly mu semi-stable object in your ML. So how does that look like? So if you have an strictly mu semi-stable object, so that means that it's going to be destabilized by some subsheaf of rank 1. So that means that the E will have to fit in an exact sequence like this. So so this E must, and this, so this is what we call a destabilizing. So the OD, so the E, so this sheaves here this is the ideal sheaf of some subscheme of length 0. And here I should have probably written a I of Z2. So I have Z1 and Z2. These are subschemes of length 0 of the surface S, and my E fits in an exact sequence like this. And because I'm assuming that this is strictly mu semi-stable, this OD tensored by this ideal sheaf is a destabilizing sheaf for E, meaning that this has the slope of this one has to be the same as the slope of this one, which is to say that we have these numerical conditions here, these intersection numbers between 2D plus L and K. Okay, so whenever you have a strictly mu semi-stable object, you get stabilizing exact sequence like this. And now here we use now the numerical constraints, and you compute the second term character of E. And so this is going to be multiplicative in exact sequences. So you compute this, this second term character, and then you get this numerical constraints on the intersection of D and D plus K and the lengths of Z1 and Z2. Okay. And so what it means is the following then. Okay, so whenever I have one such D, I get in my space of hyperplanes, I get a hyperplane defined by 2D plus K. So this is the hyperplane of all polarizations L that intersect 2D plus K in 0. And then here I noted by L minus the polarization on the negative side of the hyperplane, and by L plus a polarization on the positive side of the hyperplane. And now if you take a polarization, say in the positive side of the hyperplane, so that satisfies this condition. And this is the same thing as saying that the intersection of L plus with D is greater than the slope of E with respect to L plus, which is this number there. And so in other words, this locally distortion-free sheaf E is not stable with respect to L plus. So our object E does not live in the moduli space L plus. So what happens, so this is what we have. So for polarizations, so we have this strictly mu semi-stable object E. So this is something that lives in the moduli space ML, but if you change L to L plus, it is no longer in the moduli space. On the other hand, you can check that if you change your polarization to L minus, then one can check that in fact this is still L plus stable. And so this is, we're going to look again at what happens with this when you make this change of polarization. So for example, so this is a very concrete example. Suppose that you want to find all the extensions E that leave all the torsion-free sheaves that leaves in an exact sequence like this. Okay, so this H here, as I said, this is the pullback of a hyperplane section. Now, if you want to compute what are all the extensions of that lie in an exact sequence like this, what you have to do, the set of this extensions, these are parameterized by the X1 of one line bundle by the other. And then if you compute, and you can compute this again using Riemann-Roch, this space of extensions is Pn. So in this case here, what we see is that if you take an L on the positive side of this hyperplane, then you get this Pn as a moduli, this Pn contained in the moduli space of stable, in this case, stable locally free sheaves. In this case, because the subsheaves Z1 and Z2 were 0, so they were empty. In this case, this is really a vector bundle of rank 2. There's no torsion. Okay, so here in this way, if I take my L, my ample line bundle L in a suitable way, and I will tell you exactly what this line bundle will be soon, you get a Pn as a moduli space. Okay, so this is okay. So this is one example, but now let me say how we can do this in general. So I will define now what we call a chamber decomposition on the ample cone. So this is how I define this. So I consider as walls all the hyperplanes that are defined in this way, 2D plus K perp. And let me just go back. I'm sorry, I should probably go back a few slides here, just to show you that this, okay, so this is what I want to say. This divisor D, I choose divisors D's and this subschemes Z1 and Z2 that satisfy this condition. So I have to have that 2D plus that D intersect minus D intersect D plus K plus the length of Z1 plus the length of Z2 is 2. Whenever I have this numerical constraints, I take such a wall. So I take all these walls, I take all these walls, and now I define as a chamber the connected component of the ample cone minus the walls. So this is what I call a chamber. And then, so this is the general theory that whenever I have two ample line bundles, L and L prime, in the same chamber, they will define the same moduli space. And so what we do then is to determine all the walls, well, not all the walls for change of stability, but we determine all the walls on the side of the on the side of this space of divisors where for polarizations that intersect L negatively. So remember that if I have a P2 blown up at least 9 points, then the canonical bundle is the anti-canonical bundle is no longer ample. So I recall that we had a part of the cone in the negative part of the hyperplane that was the cone of curves, which was generated by those -1 curves. So we had something that is looks like locally polyhedral. And on the positive cone, this was a bit wild, and we did not really know the cone on that side. So we really can understand things well on the side of the cone where the canonical is negative. So these are the walls that we determine, and they correspond to divisors D that satisfy this numerical condition. So just we can just sort of try to write down, well, we don't have to do it for all of D, but in principle, you can start by finding all the divisors D for which we have this numerical constraint, and then determine these walls. Okay, so, and now, for instance, this is a claim that some of these walls are the following. So look at the walls of the form defined by K plus 2H. And the claim is that on the negative side of this hyperplane, the moduli space is empty. So in particular, so for every, so this line bundle H was obtained as a choice of realization of P2 as S of blow up of P2 at n plus 4 points. So if I now make the Weyl group act on the space of divisors, so remember we had this Weyl group, this infinite Weyl group acting on the space of divisors, I will get infinitely many walls like this. Okay, so let me prove this. That at least let me give you an idea of how we prove that these walls define this stability. These are walls for the stability. So suppose that we have some object, some semi-stable object in L0. So here by L0, I mean something on the negative side of the hyperplane. Then let's consider this E dual tensor OH. So this is always locally free, even if E is not locally free, because I took the dual. So this is a reflexive sheet, so this is locally free. And so we can compute, using Riemann-Roch, you can compute the Euler characteristic of F. So this is just a computation. And so you compute this, and then on the other hand, you know that this is the H0 of F minus H1 plus H2. And this one here, we can show that this is 0. And this was, again, for the same reason as I said before, we are choosing a polarization that has negative intersection with K. So when you write the H2 as the dual, as the A01, you find that there is really no home from E to the corresponding line bundle. Okay, so this is, and so in the end, so what you get is that this is showing us that you must have a non-zero morphism from E to this OSH. Okay, so this is just by doing some Riemann-Roch computation and using, again, Serre duality. Okay, so now, because we have a morphism like this, then again, you use the fact that the mu semi-stability to say that when you look at the image of the locally free sheaf E on a OSH, then the stability must either stay the same or must increase. And this is what it says. So this is saying that the stability, the slope is non-decreasing. And this is the same thing, and this is exactly the numerical constraints that we need. So this is saying that 2K plus H intersect L0 is non-negative. So this is the proof that so this is the sketch of the proof. So this is to show that in this way, we can find all the walls that define a non-empty moduli space. So you have a choice of H for a realization of P2 as the blow up of of S as the blow up of P2 in n+4 points. And then if you apply the Weil group now to H, and then you get all the other realizations of P2 as a blow up, and then you get infinitely many conditions on the polarization. Okay, so this is this was what we call the external walls for the stability fan. And now, in general, you have some internal walls. So these walls are going to be defined by other divisors D. And again, in this case, for each such wall, we can say exactly what happens when we cross this hyperplane in the in the stability fan. So this is what you get in general. So whenever you have a wall, you have a change in the moduli space. So you have a diagram of this form. So here I denoted the moduli space of Gieseker's stable objects with respect to L minus, and here the same thing, the moduli space for the Gieseker semi-stable objects with respect to L plus. And usually I get a whenever I have a wall, I get an internal wall, I get a morphism to the moduli space here of mu semi-stable objects with respect to L naught. And let me tell you what these morphisms do. So these are going to be birational morphisms, and let me explain what they contract. So if you look at the moduli space L minus, then this was the computation that we saw before. You look at all the extensions of this form. So this I call this subset PD. So this consists of all the extensions of this form. And this is, again, these are parameterized by some X1. And so you can, again, use Riemann-Roch to compute the dimension of these extensions. And the same thing for the other one. So here you see that you could look at these extensions and then you could switch D by minus K minus D. So if you switch D by minus K minus D, then you get what you say the opposite exact sequence. And now you look at the exact sequences that are opposite to the first one. So in this way you get this, these two extensions, these two types of extensions, and these are precisely the loci that get contracted by this morphism. So everything that was, so this, you get this set of extensions. So these are the sheaves, the objects that are semi-stable with respect to L, that are stable with respect to L minus, and then they become strictly semi-stable with respect to L0, and the same thing for the positive part. And now you see this can be computed again by Riemann-Roch, and what we get is that our D's always satisfy this condition, that the D intersect D plus K was -2, and this dimension D, little d, is just minus D squared, which is always greater or equal than 0. So this is something that we compute. So this will depend on the wall. So the wall will depend on the D, and these numerical conditions on the D, and the loci that get contracted will also depend on this divisor D. But in any case, one can, if you fix the D, you can compute these. You can compute this loci. So these are what we call the wall crossings, and this is now how we actually construct the correct polarization for our purposes. So we look at ample divisors that are of this form, LA minus K plus A times H. So these are, if you choose your, for instance, if you take A big enough, this will always be an ample line bundle. For A sufficiently large, if you take, say, make A go to infinity, and then you start decreasing, and then you check what happens with which walls you cross. So first of all, if your A was very big, then this is the computation that we saw before. You were going to be on the negative side of the purple hyperplane, so the moduli space is going to be empty. And then eventually you hit this external wall, and when you hit the external wall and then you get inside the new chamber, then the moduli space becomes Pn. And then again, you can check what are the next walls that you have to cross. And then the next walls are the green walls. So there you will have m+4 walls crossed at the same time. And these are precisely the walls that are determined by hyperplanes of the form, of the divisors of the form DI EH minus EI. So for each DI of the form H minus EI, you get a hyperplane. And when you do the wall cross, this corresponds precisely to blowing up one point. So this was the case when the D square was 0. So when you cross here, what you get is precisely the blow up of Pn at one point corresponding to each of the walls that you cross at the same time. Okay, so in this way, so this was, okay, sorry, it's the sketch of the proof. And okay, this is what I wanted to tell you. Thank you.